So remember my summary of effectively the last part of chapter 10, which was we will want to reason about the behavior, the closed loop behavior of systems, without having to go to the effort of all the way going to inverse Laplace of that actual closed loop transfer function. And if you were kind of paying attention, you noticed that many of the questions focused on the limits that are implied on the gain of the controller. And I just want to remind you that I've mentioned this before. In earlier lectures, I mentioned that we want very large gains in our controller. And the reason why we want large gains is because of this idea that the ideal controller, if you look at this closed loop transfer function, has a 0 over here. In other words, there is no effect. When D changes, nothing happens, right? And a 1 over here, which says as soon as the set point changes, in that exact same moment, the output moves to exactly what the set point was. That's perfect control. And if you look at the shape of these, you can see that one of the ways in which we can make that happen is to make GC very large. Right? So when GC becomes very large, the left-hand transfer function, the servo transfer function, goes to 1, and also at the same time, the disturbance rejection transfer function goes to 0. So infinitely large gains, if you just did that piece of the math, would be the perfect control. You can read much of the rest of chapter 10 as, oh, but wait, we can't use infinite gains. So for a first-order system with proportional feedback, that is the perfect controller. Just like use the biggest gain that you can. The bigger the gain, the better everything becomes. It's better for everything. It's better for disturbance rejection. It's better for set point tracking. It makes your system faster. It makes your teeth whiter. You know, it's the best thing ever. However, we also saw that changing these gains moves the poles of the closed loop transfer function. And most of the time, increasing gains will move the poles of the closed loop transfer function towards the right-hand plane. And eventually, at some upper bound for the magnitude of gain, typically, a bad thing happens and some of the poles move to the right-hand plane. And we want to know when that will happen so that we can find realistic bounds on K. We know probably Kc equals 0 is terrible, and we know at least instinctually now that larger gains are better in most cases. So that's where we stand in terms of finding good values for the controller gain. Now, while I've got these transfer functions on the screen, I also want you to look closely and notice that actually the gain that is actually important is not just the controller gain, but actually GC-GP. GC and GP, this kind of everything here in this loop is in both of these denominators. If I were to add extra stuff there, it would end up over here because of our feedback. And what that means is that the closed loop characteristic depends on the gains of all of the transfer functions in the loop. And in general, in order to obtain the same behavior in the loop, if anything in GP changes, and specifically if GP changes its gain, if the process changes its gain in any way. Now remember, there are more components here. If we go back to our kind of a full version of that block diagram, there's much more components. There's the gain of the transducer that connects the controller to whatever the actual final control element is. In many cases, a valve, right? So the controller itself typically will output an electronic signal. In order to convert that electronic signal to something that can actually interact with the real world, there will be a transducer, right? Transducers, remember, is just the name for something that converts one form of energy to another. So in many cases, there is a valve. In some cases, there may be like an electric element or something like that, or some other thing that can interact with that system. Whenever one of these gains changes, if I change the gain of my I to P converter, if I want exactly the same behavior of the loop, I must change the gain of the controller in inverse proportion to compensate, because the product is what is determining the behavior, right? So if the behavior is dependent on the product GC, K, GV, and GP, if any one of those elements goes down by a half, I have to multiply the gain of the controller by 2, right? If I divide something by 2 in any of the blocks, I have to multiply by 2 in the controller to get the same behavior. And that's the deep idea that links all of the questions that you answered in the TUT about which of these things, if they change, will change things. So typically, offsets, moving things up and down, or relinearization around a different point or whatever, will not change the gains. And therefore, they will not have any effect. We won't have to retune the controller. Anything that affects the gains, and this would be the spans, it would be moving to a different operating region for the controller, for the plant. For example, remember that the plant, the real plant, not our model of the plant, but the actual plant, may have different gains in different regions of operation, right? And so typically moving the plant from one region of operation to another will also change the effective gain of the plant. So all of those things, and I'm saying gain a lot because gain is the most common thing that changes. Remember, most of the small elements that we've got drawn over here, the transducers and the measurement instruments, even the valve to a certain extent, in almost all cases, those things are fast enough relative to the system that we can safely ignore their dynamics. So don't hear what I'm saying about the gains and say only the gains are important. Because obviously if the time constants change or any of those things change, obviously then the behavior will change. I mean, that's obvious that the behavior will change. But the gain changing will change the dynamic nature of the closed loop poles. And that's an interesting thing, because that is a closed loop thing. That's something that's special about closed loop behavior. I want to get back to this closed loop idea as well, as I have had a couple of questions about closed loop and open loop. Remember that open loop behavior is about whether the controller is acting upon its measurement. If you want to have one sentence summary of whether we are dealing with open loop behavior or closed loop behavior, that's the one sentence summary. Open loop behavior is when the controller is not acting on the measurement. Closed loop behavior is if the controller is acting on the measurement. Now, why would it not be acting on the measurement? For instance, if I put the controller into manual, or if I disconnect that feedback loop, in both of those cases, and so when I say disconnect this feedback loop, what does that even mean? Well, I can draw a line through it in the diagram, but I can just pull the wire out of the box, right? Like, we are trying to describe the behavior of real systems. And so if I disconnect the measurement from the box, or for instance, there's another version of this, I can take the thermocouple out of the tank, and it can just be measuring ambient conditions, right? In that case, again, we have open loop behavior. The key idea here is that the output from the controller is not being fed back into the controller in any way. That's open loop behavior. So open loop behavior if I change the gains of things in the open loop, 100% guarantee the dynamics will stay the same. When I say the dynamics here, I'm talking about the nature of the poles, of the transfer functions that are involved. If I take a probe, and it's a first order, it is approximately a first order system with a time constant of 20. If I change the gain of the probe by changing its transmitter's band, that will not affect the dynamics of that probe. The probe will still take approximately 20 seconds to get to whatever, 63% of the final value. It's different when the loop is closed. And I want you to understand this very clearly. As soon as I close the loop, changing the gains of things changes the dynamics of the closed loop transfer functions. That's a deep idea, right? Because it's new. This has never happened before. Previously in dynamics, before we had feedback loops, multiplying by numbers, by simple numbers, like changing the gains of systems, did nothing to change their characteristics on the complex plane. It did nothing to change the nature of the roots of the characteristic equation. But because I have this feedback loop, changing any one of these things, C, changes the characteristic equation. So closed loop behavior has this thing that gains of the closed loop transfer, or of the single transfer functions, may affect the dynamics of the closed loop behavior. Open loop behavior, the gains won't change the dynamics. If I have a second order system with a particular damping coefficient, if I multiply by a constant, I'll get exactly the same characteristic equation. If I have closed loop behavior, the closed loop has different dynamics depending on the gains. And so why I'm belaboring this point is because I want to make it clear that this is kind of a surprising conclusion. It wouldn't have surprised you if I said changing the dynamics of a system changes the dynamics of a system. In other words, changing the time constant of the probe will make it respond faster or slower. That's unsurprising. That's like obvious, right? If I have a first order system and it's got a time constant of 20, obviously that will behave differently qualitatively in dynamics if I to a system with a time constant of 10 or 50 or 100. But it's not obvious that just changing the gains of things will change the speed at which they respond. And this is true for these closed loop transfer functions, that simply changing the gain of the controller can make the system can change the closed loop time constant from 10 to 20. Just the gain. That's new, right? That's surprising. And so actually what we're trying to say with those problems, you saw, okay, if the gains change, the dynamics will change. If any of the gains in the closed loop change and there aren't accommodating gain changes, then we will see different dynamics.